Hello everyone, this is Professor Roman. Let's continue the group theory lectures. Now that we have discussed the family of symmetric groups, we're going to turn to the family of free groups. As with the symmetric groups, there's one free group, which I will denote by F sub x for each non-empty set x. Also, as with the symmetric groups, if x and y are sets of the same cardinality, then the free groups fx and fy are isomorphic. So there is really only one free group for each cardinality. In a sense, and this is speaking very informally, the free groups and the symmetric groups are extreme opposites of one another. On the one hand, Cayley's theorem tells us that the symmetric groups contain all possible groups as subgroups. So any behavior that appears in any group will also appear in some symmetric group. On the other hand, the reason that the free group is called free is that the free groups exhibit no additional behavior beyond what is required by the definition of a group, namely associativity, existence of an identity, and existence of inverses. So, in summary, and again very informally, and taken with the appropriate understanding, everything happens in the symmetric groups and nothing happens in the free groups. Again, except what must happen in all groups. The first step in defining free groups is to define the general concept of words over an alphabet. Let X be a non-empty set. A finite sequence, x1 through xn, of elements of X is called a word or string over X. And it's usually written without the commas, just juxtaposing the symbols. So we would write it like this. Sometimes parentheses are required to avoid any ambiguity. The set of all words over X is denoted by X star, and then X is called the alphabet for X star. The number of elements in a word, W, is called the length of W, and I'll denote it by len of W. There's a unique word of length 0 in X star. It's called the empty word and denoted by epsilon. A subword, or substring of a word W, is a subsequence of W consisting of consecutive elements of W. And a subword that's not equal to the whole word is called a proper subword. The empty word is considered to be a subword of all words. So, as an example, here's a word x, y, y, z, x. Then y, y, z is a subword because it consists of consecutive elements from W. But x, z, x is not a subword because the three letters are not consecutive in W. X, Y, Y is what we would call a prefix of W. So is X, Y, so is X. So a prefix is a subword that begins at the beginning of the word itself. So we have right now a set of words. It has no structure. So the next step is to install an algebraic structure on the set X star. And the first step in doing that is to define a binary operation, and we're going to use juxtaposition. So I called it J here. It's a function from ordered pairs to elements of X star. If you concatenate with the empty word, that has no effect. And J of UV is just the concatenation of U and V, juxtaposition of U and V. So here are some examples. Juxtaposition is associative, satisfies this property, but it's decidedly not commutative. The empty word is an identity for juxtaposition, essentially by definition here. So X star is a monoid under juxtaposition where the empty word is the identity. Also, it's customary to allow the use of non-negative exponents when writing words. So x to the power n is just the juxtaposition of n copies of x. X to the power 0 is by definition the empty word. But it's worth keeping in mind that this is just a notational convenience. Literally speaking, x squared is not a word. It's the abbreviation for the word XX. That may seem a little pedantic, but it's important to keep things as precise as possible here. We'll refer to something written with exponents as a word, but we keep in mind that there's an abbreviation going on there. Well, the monoid X star is as far as possible from being a group as it could be for any monoid, because only one element has an inverse, and that's the empty word. No other elements have inverses. We're a long way from a group. But we can obtain inverses and a group structure with only a modest amount of bother, really. And what we're going to do involves both partial orders and equivalence relations. And so this will be very good practice in seeing how those two concepts are used. And something that's a bit remarkable is that both of these relations, partial orders and equivalence relations, appear in a natural way at almost the same time. I haven't seen that too often in mathematics. So, to get inverses, the first step is to adjoin some new symbols that can provide those inverses. So let X be a non-empty set of formal symbols and assume that each little x in X, that for each little x in X, the symbol X inverse does not appear in X. We can always arrange that. These are formal symbols. We can change the symbols if we need to. So this assumption is correct. Then we define capital X inverse to be the set of all formal symbols that look like this, little x inverse for X in capital X. So by assumption, X and X inverse are disjoint. So their union is called a disjoint union. That just means it's a union whose participants are disjoint. And there's a symbol for disjoint union. It's similar to the union symbol, but instead of having a rounded bottom, it has a flat bottom. This is, I think the term is cup for this symbol. So now we consider the monoid formed by taking the words over this disjoint union. So now we have available symbols little x and little x inverse. And these symbols, the little x inverses, are intended to provide inverses, but we still have an issue we have to deal with. We'd like the group product to be juxtaposition, but this won't allow inverses, except for the empty word. Because when you juxtapose a non-empty word with any other word, you do not shorten its length. So you're not going to get the empty word by juxtaposition. So in particular, there's nothing we can do at the moment with this word XX inverse. We can't do anything with it. It's not the empty word. The way out of this dilemma, the way to resolve this issue, and this is quite common in mathematics, is to identify distinct formal words as being the same element of what we will eventually call the free group. So while these two words, XX inverse and epsilon, are distinct in the monoid, we want them to represent the same element of the group, fx, which would give us this relation. In mathematics, the way you make identifications, which you do quite often, is to use equivalence relations, because they are a generalization of equality. They have the three properties that equality has. This definition is going to come in quite handy to help us discuss in our discussion here. We'll refer to these two words, XX inverse and X inverse X, as inverse pairs. And a word in F, the monoid F, that has no inverse pair subwords we'll call inverse pair free. So this word, xy, x inverse z, is inverse pair free, but this word, xy, xx inverse z, is not inverse pair free. Now we can take the first step towards obtaining inverses by defining a binary relation on the monoid F using what I'm going to call removal rules. So if we have two words u and v in F and a symbol little x in X, then we can pull out this inverse pair. We can pull out or remove this inverse pair. We can remove this inverse pair if it's all by itself in the word, and it'll produce the empty word, and similarly for this one. U and V, one of U and V could be missing also, so you might get rules that look like this. So these are the removal rules. And if we have two words in the monoid, U and V, any sequence of n applications, n could be 0, of removal rules that sends U to V, I'm going to call a removal sequence of length n from U to V. And the removal sequences of length 0 we'll refer to as trivial sequences. And we will also say that V is a reduction of U when there is such a removal sequence. And V is a strict reduction of U if the removal sequence is not trivial, so we pull out at least one inverse pair. Now, reduction is a binary relation on F. And so if V is a reduction of U, it comes from U by application of 0 or more removal rules, we will write V less than or equal to U. And I'll explain why. You'll see why this notation is appropriate in just a minute. And if v is less than or equal to u, but u is different from v, then we'll write this as a strict inequality, v less than u. Reduction is reflexive because you can always use the trivial removal sequence. So a word is can be reduced to itself. It is transitive, but it's not symmetric. In fact, if u is a reduction of v and v is a reduction of u, then u and v have to be equal. So reduction is anti-symmetric and therefore a partial order. And I will leave you to think about a proof for this. Okay. You can think in terms of the lengths of the words. Now, by definition, an element mu in F is minimal under the reduction partial order if mu cannot be strictly reduced to a shorter word. So minimal words must be inverse pair free, because otherwise you could pull out an inverse pair and reduce further. Conversely, any inverse pair word is minimal because you can't apply any removal rules. So you can't find anything less than or equal to that word. So the minimal elements in the monoid under the partial order of reduction are precisely the inverse pair free words. And this should not come as a great surprise. Okay. So here's the theorem. Let X be an unempty set and let F be this monoid. Reduction is a partial order on F. A word in F is minimal under the partial order if and only if it is inverse pair free. For every word W in F, there is a minimal word, which I denote here by W sub m, that is a reduction of W. And this final statement follows simply from the fact that we can repeatedly remove inverse pairs from W until this is no longer possible. Every time we remove an inverse pair, the word gets shorter. We reduce the length. And so that has to stop at some point. And the result then is an inverse pair free word that is less than or equal to the original word under reduction. So we didn't get the equivalence relation we were looking for, but we did obtain a partial order. Fortunately, we can get symmetry and therefore an equivalence relation simply by allowing the corresponding insertion rules. These are the rules that go in the opposite direction from the four removal rules. So we will refer to any sequence of n, again n could be 0, applications of removal and insertion rules that starts at u and ends at v as a reduction expansion sequence from u to v of length n. And again, when n is 0, we get the trivial reduction expansion sequence. Reduction expansion is an equivalence relation on the monoid F, and I'll denote it by this squiggly line. and I'll call it word equivalence, for lack of a better term. Word equivalence, being an equivalence relation, defines partition of the monoid into word equivalence classes. So all the words in a given word equivalence class are word equivalent, which means you can get from any one to any other one by a reduction expansion sequence. But you can't reach anything outside of the equivalence class using such sequences. But because F is partial order under pure reduction, each equivalence class is also a partially ordered set under reduction. And what the previous theorem told us was that there's at least one minimal, or equivalently inverse pair free, word in each word equivalence class. Well, then it's natural to wonder if there is a unique word, which I know there's one, mu sub e. Is this unique? If that were true, then all the words in the equivalence class E could be reduced to mu sub e. In other words, mu sub e would be less than or equal to all words in the equivalence class under reduction, and so mu sub e would in fact be the minimum element in the equivalence class E. Every equivalence class would have not just a minimal element, but a minimum element. So suppose that mu prime and mu are minimal words in one of these equivalence classes, the word equivalence classes. We know that there is a reduction expansion sequence from mu prime to mu. If we could show that there's also a pure reduction sequence from mu prime to mu, then because mu prime, the starting point, is inverse pair free, the reduction must be trivial, and so mu equals mu prime. In fact, it seems quite reasonable that if there's a reduction expansion sequence from any word W to an inverse pair free word mu, then all of the insertions in the sequence must at some point be undone. And so perhaps no insertions were necessary in the first place. So what we suspect and would need to prove is that if W is word equivalent to mu, and so there's a reduction expansion sequence from W to mu, and mu is inverse pair free, then mu is in fact a reduction from W. So to prove this, suppose we have a reduction expansion sequence of length n from W to mu. Not knowing what to do next, we would turn to the extreme witness principle, which I discussed at the beginning of these lectures. And it suggests we look at an extreme witness to the insertions. We're hoping that we can eliminate the insertions and get a pure reduction. There is the first insertion and there's the last insertion. Those are extreme witnesses. The first insertion isn't going to help too much, but the final insertion will help. So let's concentrate on the final insertion. I have to remove this. There's a little error there. So our goal is to eliminate the final insertion and therefore reduce the number of insertions in the original reduction expansion sequence. If we can do this, then we can repeat that process and remove all of the insertions, eventually arriving at a pure reduction sequence from W to mu. Well, suppose that the final insertion occurs at step K in the reduction expansion sequence. So step K looks like has one of two forms. There's a word, and write it as UV, and you insert here XX inverse between U and V. One of these two might be empty. Or you insert X inverse X. And the argument we're going to give is the same essentially in both cases, so we'll just consider the first possibility here. So the final insertion inserts X inverse somewhere in the word, and U comes before and V comes after. Since this is the final insertion step, these two symbols, X inverse, here in this inverse pair, are never separated in the remaining portion of the reduction expansion sequence. There are no more insertions. But since mu is inverse pair free, this substring that we inserted at step K must be eliminated by a subsequent step in the process. And by that I mean at least one of the two symbols, X or X inverse, has to go away. Now the next several steps in the process, which are all removal steps, from now on it's just removal steps, may reduce one or both of the U and the V. It may not have anything to do with the inverse pair XX inverse. Okay? So at some point though, which I'll say is step M greater than K, this inverse pair has to be eliminated. So the intermediate steps, step K plus 1 through M minus 1, act only on U and V. And they might do something like this. U XX inverse V will go to U1 XX inverse V1, where U1 is a reduction of U, V1 is a reduction of V. Could be trivial reductions. One of them could be trivial. Then this proceeds through to step M minus 1, which further reduces the subword that comes before the inverse pair and or the subword that comes after the inverse pair. So simplifying the notation, we will eventually arrive at a word that looks like this, U prime XX inverse V prime, where U prime is a reduction of U and V prime is a reduction of V. Now we are at step M, the destruction step for this inverse pair. There are only three possibilities. The most obvious one is just to yank out XX inverse. And so that will take this word to U prime, V prime. Another possibility is that there's an interaction between the inverse pair and either U prime or V prime. Look here. Maybe U prime ends in X inverse. And then we have an opportunity to remove x inverse x and not touch this x inverse. So u prime could be u double prime x inverse, and so we now have u double prime x inverse x inverse v prime, and we could pull out x inverse x, leaving this, but observe we're back to u double prime x inverse. What we did is we swapped one x inverse for another, and so that's still u prime v prime. Similarly, v prime could start with an x, be x v double prime, and we pull out this inverse pair, but again we will still get u prime v prime. So no matter how we destroy xx inverse, whether we just pull it out or whether we allow it to interact with u prime or v prime, if it does, and pull out a different inverse pair, we're going to end up with u prime v prime regardless. To get from u to u prime had nothing to do with the inverse pair we inserted at step k. Same thing for the removal sequence from v to v prime. So what we could have done to arrive at u prime v prime is never having inserted xx inverse. Skip step k. You could put a little space in there, in that word where xx inverse went, if you want, if it helps make it clearer. And then do the intermediate steps that before we skipped step k would have been labeled steps k plus 1 through m minus 1. Do those steps. They act only on u and v. They don't touch anything else, and arrive at u prime v prime. And we also then get to skip step m, because we didn't put in the inverse pair in the first place. We don't need to take it out. It's not there. So we have shortened, we have removed the final insertion, and as a consequence actually removed a later step. So we have one less insertion in the reduction expansion sequence. So again then, by repeating this argument, we can produce a pure reduction from w to u to mu. And that proves the result we were looking for. That was, where'd it go? Oh, right here. That was this statement here. So it follows, as we said, that each word equivalence class contains a minimal element, a unique minimal element, a unique pair-free word. This should be, I forgot the word unique here. Okay, I put it here, but I forgot to put it there, so whatever. Okay, this unique inverse pair-free word, which I denote by mu sub e, is also the unique shortest word in the equivalence class, because all other words can be reduced to mu sub e, and if they're not equal to mu sub e, the reduction is strict. Something has to be removed. Okay. If you had another word that was the same length as mu sub e, you couldn't reduce it to mu sub e unless it was equal to mu sub e. So let's summarize and add one more fact. Let X be a non-empty set. Let F be this monoid. Reduction expansion is an equivalence relation on F, which I'm calling word equivalence. Reduction is a partial order on F, and the minimal elements of F under this order are precisely the inverse pair free words. Every word equivalence class contains a unique minimum word, mu sub b, which is also the unique shortest word in E, and the unique inverse pair free word in E. So it has all three properties. It's unique minimum, unique shortest, unique inverse pair free. Any word W in E can be reduced to the unique inverse pair free word mu sub E. All we have to do is remove inverse pairs until that's no longer possible. This is something we haven't discussed. A non-empty word W in F is inverse pair free if and only if it can be written in this form: x1 to the e1 through xn to the en, where the consecutive x's are distinct. So if two x's are next to each other, they have to be distinct. Otherwise, you would have combined them. And the integers e sub I are non-zero. If an integer is 0, you drop that factor because it's the empty word. Okay. So that's a concise, constructive expression for the inverse pair free words. And throw out all the inverse pairs and combine everything as much as you can, and you'll have it this form. Another way to look at this is that the inverse pair free words form a system of distinct representatives, often abbreviated SDR, for the partition defined by word equivalence. Now, at last, we can provide a definition for the free group, f sub x. And there are other definitions, and I'll allude to that a bit later. Let X be a non-empty set, and let Fx be the set of all inverse pair free words over this alphabet. So we include the empty word and all words of this form, which is the equivalent to saying all inverse pair free words by the theorem we looked at earlier. Okay. Then this set is a group under the operation that consists of juxtaposition followed by reduction. Juxtaposition alone won't do it, as we talked about earlier, because it doesn't shorten anything. But we can then reduce, and that is the group operation. We get a group called a free group on X. And the elements of X are referred to as generators of the free group. So Fx is the free group generated by X. Most people would say the free group on X. And I'll write the identity rather than using epsilon as 1, because that's often what people do. So, as to proof, we need a notation for this operation, juxtaposition followed by reduction, so I'll use an asterisk or star. And I will leave it to you to show that epsilon is the identity under this operation, and that every word has an inverse. That's easier than it might appear at first. Associativity is the tricky one. So let us denote by W sub R the unique inverse pair free word that is word equivalent to W. W's in the monoid. Rip out all the inverse pairs until you can't do it anymore. You get W sub R. And you get the same word W sub R no matter what W started with, because it's the unique minimum word in the equivalence class. Then, if we have two words in the monoid, this obtains. We reduce U, we reduce V, take their product, juxtapose, and then that juxtaposition may create additional inverse pairs. So we have to reduce again. That would be the same as if we just juxtaposed U and V and then reduced. This reminds me of a similar equation with regard to taking residue classes in the integers. If you have two integers I and j, let's say, and you take I mod n times j mod n, and then you reduce again mod n, you wasted your time because that's the same as just ij mod n. You didn't need to take the first two reductions mod n. It works the same way here. Reducing u and reducing v were not necessary as long as you reduce after you take the product. Why is this true? Well, the words uv and urvr are word equivalent because there's a reduction from u to ur and a reduction from v to vr. Just do both reductions one at a time, and you will get from uv to urvr. And so these are word equivalent. That means they belong in the same word equivalence class, and so they are both word equivalent to the same inverse pair free word, which is this or this. So with this formula, the rest is relatively simple. If we do this operation in this order, we do u star v, then we do star w, what we are doing is reducing uv, then juxtaposing by w. So actually I should have said, first we juxtapose uv, then we reduce that is u star v, then we juxtapose w, and then we reduce that, so we get this. Okay. Well, we can reduce w here before we do this final reduction. So we now get this, but this, according to the formula here, is equal to this. If we do it the other way, if we reassociate, this is something you might want to write up for yourself before you read this, you'll end up with this, but because juxtaposition is associative, these two are the same. So this operation of juxtaposition followed by reduction is associative, and therefore it's a group product the other properties fit, and we have ourselves a group called the free group on X. This is a constructive definition of the free group. It shows us exactly what the elements look like. The simplest case of a free group is the free group generated by a single element, little x. And that is the monoid consisting of all words over the alphabet XX inverse with the operation of juxtaposition followed by reduction. What do we get? The powers of x. We get the integral powers of x, all integral powers of x. We get the infinite cyclic group generated by x. On the other hand, and you can see in that cyclic group, nothing's going on except what has to go on in a group, namely associativity, identity, and inverses. Okay. On the other hand, the free group on two generators, distinct generators, this already is very complicated. It's easy enough to write down the elements of the free group according to our definition, but working with that group becomes very difficult because there are no algebraic relations. And that will become much more apparent much later in this course. When we get to chapter 6, we're going to see an example related to finitely generated groups and subgroups. And we'll see just how tricky it is to work with free groups, despite the fact that, informally speaking, nothing is going on there except what has to go on. That's a little misleading. It does not mean that free groups are easy to work with. In fact, while it might seem intuitively clear that every subgroup of a free group is free, if nothing's going on in the whole group except what has to go on, probably nothing's going on in the subgroups. That is true, but the known proofs are very complicated. The known proofs that subgroups of a free group are free. This theorem is called the Nielsen-Schreier theorem. Nielsen proved the result for finitely generated groups, finitely generated subgroups of a free group in 1921. It wasn't till 6 years later that Schreier generalized it to all subgroups of a free group. So this is a bit tricky stuff. I mentioned that, sort of alluded to this fact when I said earlier we can provide a definition of the free group. There are other definitions. One of the most common definitions of free group is not constructive. It happens that free groups satisfy a property that characterizes them, and it's a very important property because it is often the property you use when dealing with free groups rather than the actual elements themselves and what they look like. So the non-constructive definition involves the concept of universality. And that's a topic that pervades all of mathematics, even though it's not expressed this way very often. It's a property that sort of belongs to a branch of mathematics called category theory, and you can learn about universality in the general context if you're interested by looking at my category theory lectures on YouTube. I want to just very briefly give you the sense of what this is. And the best way to do that is actually to draw an analogy between the free group situation and linear algebra. So if you watch my linear algebra videos, you'll know exactly what I'm talking about. Hopefully, if you've taken a linear algebra course, an upper division course, maybe even lower division, I'm not sure, you will have encountered the following theorem. I emphasize this theorem very strongly in my linear algebra courses, except maybe at the very lowest level. Let V be a vector space with basis B, and let W be a vector space. Then any set function, f, from the basis B to the other vector space W can be extended to a unique linear transformation, f, from V to W. I maybe should have worded that a little differently. It can be extended to a linear transformation, f, and it's the only extension. Okay. So in essence, linear transformations are uniquely determined by their action on a basis given by a set function. This property could be described, and I describe it in my book, in my course, as the universal property of vector space bases. Okay. Well, as it happens, a free group, f sub x, plays the same role as the vector space V, and the generating set plays the same role as the basis B. Specifically, let f sub x be the free group on X, and let H be any group. Then any set function sigma from X to H can be extended to a unique group homomorphism from Fx to H. And this is called the universal property of free groups. Okay. Well, here's the point. If G is any group that contains a non-empty set X, and if G has this universal property that I just described, in other words, if any set function from X, the subset of G, to H, can be extended to a unique group homomorphism from G to H, so G has this universal property, then G is isomorphic to a free group. And so we could refer to G as a free group. In other words, this property characterizes free groups.